Welcome back to The Explainer. Today, we're talking about line coding schemes, NRZ, RZ, Manchester, and Differential Manchester. We are diving straight into the absolute physical foundation of the internet, the very bottom of the OSI model. By the end of this, you're going to know exactly how raw data physically travels across a wire. Because, it's one thing to write a piece of software or send an email, but how do those ones and zeros actually get from your machine, travel through a physical copper wire, and end up at a server halfway across the world? Well, that is exactly what we're uncovering right now. But before we get into the clever solutions, we really have to wrap our heads around the core problem, and that is, without a shared clock, how on earth do computers count bit durations? Just imagine a sending computer wants to transmit 5 binary ones in a row. Simple enough, right? To do this, it raises the voltage on the physical copper wire to, let's say, 5 volts. But on the receiving end of that cable, the other computer just sees this continuous, unchanging block of 5 volts. How does it know if that's one really long one, or 3 ones, or exactly 5 ones? If their internal clocks are even a tiny, microscopic fraction of a millisecond out of sync, the receiver might sample that signal and read 4 ones, or maybe 6 ones, instead of the 5 we actually sent. This right here is what we call the missing clock problem in networking. It's a massive struggle for synchronization. The receiver is essentially flying blind in a sea of voltage, just desperately trying to figure out exactly when one bit ends and the next one begins. So how do we fix it? Well, the brilliant solution to our missing clock problem is line coding. By definition, line coding is simply the process of converting digital data, those pure, raw binary zeros and ones sitting inside your computer's memory, into digital signals, which are the actual physical voltage fluctuations on a wire. We aren't just blasting raw voltage down a cable willy-nilly and crossing our fingers that the other side figures it out. No, we are formatting that voltage in a very specific, rhythmic way to completely solve those synchronization issues. Think of it kind of like using a flashlight to send a message across a dark field. If you just leave the flashlight on, the person on the other side just sees a steady, boring beam of light. But if you take that basic beam and turn it into a complex Morse code, the rhythm itself brings its own timing. Line coding is basically the electrical version of that Morse code. I want you to literally visualize the journey of a single piece of data as it leaves your computer right now. Step 1, we start with your digital bits. These are the pure, raw zeros and ones generated by your software, whether you're making a web request or streaming a video. Step 2, a line coding scheme is applied. You can think of this as the translation rule, or the encoder chip inside your network interface card. This chip looks at your binary bits and decides exactly how the electrical voltage should dance to represent them. And finally, step 3. The voltage signal actually goes out on the physical wire. Your data is literally riding the voltage ups and downs. The receiver on the other side is going to read these specific, perfectly timed voltage changes, run that translation rule in reverse, and perfectly rebuild your original zeros and ones without losing a single drop of information. Now, when we look at our major translation rules, the most basic approach is NRZ, or non-return to zero. In this scheme, a 1 might simply be a high positive voltage, and a 0 is a low or negative voltage. The key to understanding this is right there in the name. The voltage never returns to a neutral 0 volts during a bit. It stays high or low for the entire duration of that bit's time slot. But hold on, think back to our missing clock problem for a second. If you send 100 ones in a row using NRZ, you just get a flat, unchanging high voltage. Synchronization gets completely lost because there are no changes for the receiver to actually lock onto. To fix this massive flaw, engineers created RZ, or return to zero. Notice the critical difference here. RZ forces the voltage to drop back to 0 volts halfway through every single bit. That little mid-bit dip to neutral 0, that acts as a built-in ticking clock. Every single time the receiver sees the voltage hit 0, it knows exactly where the middle of the bit is. Boom. This keeps its internal clock perfectly synchronized no matter how many ones or zeros are sent in a row. Okay, so looking at this comparison, we already know NRZ has poor synchronization. And RZ fixes this, but it actually introduces a whole new problem. RZ requires 3 different voltage levels to function: high, low, and 0. Managing 3 distinct electrical states takes significantly more bandwidth and power on the physical hardware, which is just not ideal. This brings us to the absolute gold standards of basic networking: Manchester and Differential Manchester encoding. These schemes are, quite frankly, brilliant. Instead of relying on a completely separate 0 voltage level to keep time, Manchester encoding ensures there is a voltage transition, either dropping from high to low or jumping from low to high in the exact middle of every single bit. So a high to low drop might mean a 0, and a low to high jump means a 1. That mandatory mid-bit transition guarantees excellent synchronization because it happens every single time. It brilliantly serves as both the data itself and the ticking clock. Then we have Differential Manchester, which takes it one step further. It still has that mandatory mid-bit transition purely to keep the clock synced, but the actual data is represented by what happens at the very start of the bit. A transition at the start might mean a 0, while no transition at the start means a 1. By separating the clock transition from the data transition, this scheme becomes incredibly robust against electrical noise and accidentally reversed wiring. It's a real game changer.
So let's bring this whiteboard theory back to the real world. Why does this actually matter to us, or to a network engineer? Well, classic Ethernet, the original 10 megabit networks that basically built the foundation of the modern internet, relied entirely on Manchester encoding. Every time you plugged in one of those older, chunky network cables, you were relying on those exact mid-bit voltage transitions to send your data across the room. Now, as we move to fast Ethernet, gigabit speeds, and beyond, we couldn't just use basic Manchester anymore, mostly because that mandatory mid-bit transition requires a massive amount of frequency bandwidth. But modern networks use highly advanced line coding derivatives that are all spiritual successors to these foundational concepts. And crucially, all of this resides purely in the physical layer. That's layer 1 of the OSI reference model. Before we can ever talk about IP addresses or routing protocols or TCP handshakes, we absolutely have to make sure the physical electrical voltage on the wire can be reliably generated and understood.
All right, pop quiz time. Let's do a quick mental check to see how well these concepts are sticking. Which line coding scheme returns to a 0 voltage level in the exact middle of a bit duration to help with timing? Think back to the naming conventions we just talked about. It's not the one that stubbornly stays high or low, and it's not the one flipping between high and low like Manchester. It's the one that explicitly drops to a neutral state to give the receiver a predictable heartbeat. Got it? If you said RZ or return to 0, you absolutely hit the nail on the head. Recognizing how that single 0-volt drop solves the missing clock problem means you are already mastering the core challenges of Layer 1 networking. We have covered a lot of ground today, from the fundamental missing clock problem all the way to the brilliant electrical engineering of Manchester encoding. But as we wrap up this explainer, if you remember only one thing, remember this: bits need a ride, and voltage provides it with a built-in clock. Line coding isn't just some dry textbook definition to memorize for an exam and forget. It is the fundamental translation that makes all digital communication physically possible across copper and fiber, the whole shebang. So the next time you plug in an Ethernet cable or think about massive streams of data flowing across the world, ask yourself, what silent, invisible voltage dance is happening right this very second to keep everything perfectly in sync? Keep that curiosity alive, keep exploring those network protocols, and I'll catch you in the next explainer.